We consider the problem of localizing and collecting observations at the global maximum of an initially unknown continuous environment with a robotic vehicle, the maximum sequence sample problem. We can formulate maximum sequence sample as a partially observable Markov decision process, or POMDP, with continuous state and observation spaces. An example of this problem is finding and sampling the shallowest coral head in this reef with an autonomous surface vehicle. Overlaid on the aerial photo is the bathymetry map of the region. If this map is known, the robot can immediately navigate to the maximum, marked with a star, and collect samples. However, in the vast majority of applications, we have no map, and must adaptively trade off between exploring to gain knowledge and exploiting high-valued samples. One of the most common sampling regimes in environmental science is non-adaptive lawnmower search. Though the method can yield a good posterior estimate of the world map, it suffers from sample sparsity in regions of interest, as indicated by the histogram. State-of-the-art baselines make use of heuristic reward functions to guide decision-making, like the upper confidence bound, or UCB. Both greedy and non-myopic strategies can be inefficient in multimodal distributions, converging to local maxima, or touring between them. We introduced the Plumes Planner, which solves the maximum sequence sample POMDP and leads to efficient convergence to and sampling from the global maximum. In this paper, we introduced two key ideas that enable Plumes to perform robust maximum seeking and sampling: continuous observation Monte Carlo tree search, and the maximum value information heuristic reward for robotic applications. Continuous observation MCTS performs non-myopic search over continuous belief states in a tree rooted at the robot's current belief and consists of three phases: selection, forward simulation, and reward back propagation. During the selection phase, a feasible action is chosen with a search heuristic which balances high average reward and number of visits. Forward simulation generates new belief nodes from the observation model. When the planning horizon is reached, accumulated reward is back-propagated to the root, updating all the simulated nodes to reflect the rollout. The key property of continuous observation MCTS, which allows for stable and robust search in continuous domains, is progressive widening, which allows observations to be visited multiple times, ultimately improving value estimation of action sequences. The action child from the root that is visited the most often by the tree search is selected for execution. This action can be proven to converge to the optimal action as the number of rollouts increases. Our second contribution is to introduce maximum value information reward to guide, explore, exploit behaviors. MVI is approximated by sampling potential maxima, shown as red stars, from the current belief of the robot. Initially, sampled maxima are uniformly distributed, and exploratory behaviors are rewarded. As observations are collected, the samples converge, and the approximate reward actually changes over time to put all expected reward at the estimated location of the global maximum. The initial exploratory behavior is similar in UCB baselines. However, UCB converges to the form of the underlying distribution, which can allow visits to any local maxima to accumulate high reward. Recalling our earlier example, we demonstrate that Plume successfully guides a small ASV to localize the most exposed coral head in a region of Bellairs Fringing Reef, Barbados. Taken together with simulation results in a diverse set of environments and theoretical performance guarantees, Plumes is a compelling new option for adaptive maximum sequence sample with mobile robots.